Today, I'll be talking about the future of global numerical weather prediction, or GNWP, a little bit on what is numerical weather prediction. Numerical weather prediction is solving the equations of motion, thermodynamic equations, and also other parameterizations, for example, ocean, ice, land interactions. Pretty much anything can be predicted with this method to relatively good accuracy, and I'll be talking about the improvements that this can make in the context of global NWP. So, improvements are needed for resolution. According to the NOAA website, the GFS, the Global Forecast System, runs with a horizontal resolution of 28 kilometers and a 3-hour time resolution. I believe that's likely when it says that on their website, it's referring to probably around 0 to 1 days in between that range, because then they mention up until about 8 days, they use 1 degree resolution, which is around 110 kilometers if you're looking at the equator, for example. And then they step up to 2.5 degrees or 275 kilometers, and then a 12-hour temporal resolution for days 8 to 16. But they mentioned this 28 kilometer one, so likely it's within a day or two of the 1 degree one that they refer to. And additional documentation also shows, as of 2021, that GFS, using its new dynamical core F3 core, has a capability of 13 kilometer resolution and 127 vertical levels. And they didn't mention time resolution, but it's also likely 3 hours. The issue here is to accurately resolve convection, which has been shown in regional models and idealized simulations. To resolve these processes, we need to go sub 3 kilometers global resolution with a time resolution of 30 to 60 minutes at the very minimum. And as you saw before, it's 110 kilometers for the first 8 days. If you're doing the high resolution one, it's 28 kilometers. It's still much higher than 3 kilometers. And additionally, in the far future, I hope to see 500 meters to 1 kilometer horizontal resolution and a 5 to 10 minute time resolution. From my experience with high resolution modeling, this is pretty good for showing convection. Ideally, in a perfect universe, 1 meter would be something that I would love to be very happy to see. But of course, I to be realistic, I think this 500 meter to 1 kilometer resolution is sufficient for my goals. Again, just to reiterate why use a global model, well, models like North American model can have their inaccuracies because their boundary conditions still depend on weather from other regions, and instead they just use the forcing at the boundaries. They kind of hope, okay, if we put our data in and then run the equations, that it should be sufficient. But my belief is, there's still, everything's connected and influences each other in the atmosphere and also ocean. And also, like, for example, convective systems are influenced by synoptic forcing that can extend beyond 1,000 kilometers. So that's kind of a point to show that their influence at the edges of this model are actually pretty important, and resolving exactly how that comes through the boundary is important. So what I stand for kind of is just do a global model. There's no boundaries you have to worry about, except the surface and the top of the atmosphere, and also the surface of the ocean. Also, using global models can provide a better context for understanding convection at a global scale, which could help solve the convection problem, which is an issue where numerical weather models that are used commonly by, for example, Met Office in Britain, National Weather Service in US, they can't really show exactly what's going to happen with convection to a great degree of accuracy, and sometimes the results are, in my experience, extremely far off. To go even further, a unified forecast system that integrates Earth processes like air-sea, land-atmosphere, land-sea, and ice-ocean, etc., these interactions would help improve our understanding of weather systems and enhance forecast accuracy because, for example, air-sea has a huge effect on convection, for example, and the weather. And ignoring the ocean, which holds a lot of heat, stores a lot of heat from the Earth, and can release it in terms of latent heat, evaporation, all this stuff, or evaporation, which later becomes released as latent heat in thunderstorms. These, including these, would be the most perfect, in my opinion. So as for improving computation, I think we should shift our models computation to GPUs to accelerate calculations. From what I've found online and heard from other people with experience in this field, 42 times faster is usually what is quoted for GPU versus CPU. Now, CPUs are still, I think, should be reserved for serial processing tasks because GPUs just aren't really built for that, and CPUs are kind of optimized for that. You can still put the GPUs on the numerical mesh calculations, which is the bulk of the calculations in atmospheric science and numerical weather prediction, and increasing that 42 times would be amazing. Kind of just to go into a little bit, what is a GPU? Why is it used for this? Because most people probably think, okay, GPUs are used for movies, they're used for video games, the kind of things that weather prediction is working on is kind of these grids that you see when you look at a picture or you look at a video. So there's actually kind of a relation here. And if you look at, a video game, one of the 3D ones that we have nowadays, every single object, like maybe there's a chair inside of the video game, each point is represented and there's calculations that have to be done to update where the location is, what color it has, and if the character in the game or you're moving through the scene, everything has to be updated and its location has to stay in the same place, and there are some calculations that are done for that at every single point. And so GPUs are literally built for this. So I think we need to move to that. Currently, we're pretty much using only CPUs. And just imagine if 42 times the GPU, if we get that speed boost, and imagine if that translated directly to 42 times higher resolution, because in essence, it kind of does. If you're able to do things 42 times faster, then you can do 42 times more things. And so maybe it's a little bit of a bold estimate, but definitely realistic. Imagine if we're doing the high resolution GFS run at 28 kilometers, divide that by 42, I think it's about 0.6. That is sub 1 kilometer, which is way below the 3 kilometers that I talked about earlier. Additionally, the 1 degree one, you divide that by 42, that's about 2.6 kilometers. That would be amazing. I also imagine that kind of using a best supercomputer system available just exclusively for global numerical weather prediction, like for example, GFS only runs on the supercomputer and nothing else, and then equipping it with the best cutting edge GPU technology and also parallel processing with the GPUs. Well, GPUs kind of already do that, but include like a whole array of GPUs. That would be kind of my dream. But then there's kind of just one caveat though, is that there's something called linear performance issues, which means you increase the number of processors, you expect it to be linear, it keeps getting faster and faster and faster, but there's actually a cutoff, and in fact it can even slow down the simulation if you include too many CPUs or GPUs. The picture here on the right is showing the GRAF model, which is it's a private company called Weather Company. They're kind of one of the people who I think they made the first GPU accelerated supercomputer, which the government currently doesn't. Their model doesn't. GFS is not a GPU of it. enabled, and I think it really should be. But here's just to show the difference between the 13 kilometers and a 30 kilometer resolution. You can see kind of on the coast, actually I'm not sure what location on Earth this is looking at, but if you look on the west coast of this landmass here, you can see how it resolves these convective updrafts and eddies really well, actually. And just to clarify what I mean by resolve, I mean break any section, like a length of this storm, and then break it into 4 parts. That would be any atmospheric process. If you can break into more than 4 parts, that would be resolved. And yeah, so a future thing that I'm really passionate about is MPAS-Core, which is we talked earlier about this GFS core. Where was it? Yeah, FE3 core. This is a different one. FE3 is still a square model, but MPAS is an unstructured grid, so it's mainly comprised of pentagons, hexagons, also some 7-sided shapes, and it has many, many benefits. And currently, based on what I've heard, originally the plan was to use FE3, but I think a revote was done, or a new vote was done, and MPAS is looking like it's going to be the thing that's used for GFS. So here are its benefits. The unstructured grid allows it to have a better representation of Earth's geometry with consistent periodic boundaries across the entire domain. One of the issues of the cube models is it's kind of like you're doing a weather prediction on a piece of paper, and when air goes across one boundary and it has to come out the other in the horizontal, when you try to make these boundary conditions, the corners have issues, and those corners connect where the poles are. So you end up having this thing called the pole problem in numerical weather prediction. So allowing periodic boundary conditions, which means every single grid cell, which is one of these hexagons, is connected to the one right next to it, and you can form a mesh around the entire Earth system. And also allows for better regional zooming. In the picture on the top right, you see that over the United States, you can actually zoom in the resolution, and still the model is what's called conservative, which means the flow is conserved, even when you're doing the zooming. And so it's better representing flow across multiple scales. That's what MPAS is called, model for prediction across scales. Also, these increased number of cell edges from 4 for a square to 5, 6, or 7, it reduces the effect of the sharp grid vertices, the corners of each grid, so you can have a better distribution of flow across more grid cells, more edges, in a way. And it also allows for a smoother, more accurate resolution of fluid dynamics, particularly effective for capturing the natural rotational shape of flows, because you can have a flow come out of one corner, go into the next shape and back in, rather than having to go through multiple more shapes just to get back to where it was. In essence, you're improving that capturing of the rotational nature of the weather phenomenon. Also, there's improved numerical accuracy due to better conservation of physical quantities, also related to the consistent boundary conditions I discussed earlier. There's also minimization of interpolation errors. When you try to get what is the value of velocity at a single point, you take an average across all of these edges, you'll get a better representation than just using 4 edges. And also, less resolution is needed to accurately resolve flow, similar, again, related to the rotational nature of these flows. Next is Unified Forecast System, UFS. This is I believe the plan currently is to replace GFS with UFS. I think currently the way it's working with GFS is kind of a big mess, and I think this is a kind of a way of cleaning it up. and also allowing us to continue improving our weather prediction and not kind of get stuck in the same place. And I'll talk a little bit about the downsides of GFS currently and why UFS is also better as well. So the Unified Forecast System is a framework for modeling Earth systems. So it includes not just the atmosphere, but also all of the processes I talked about earlier, like land, sea ice, ocean, everything that you could possibly, that we have the current knowledge about, which most of which actually we kind of do. There's just kind of an issue of perfectly representing these things, which the weather is currently much better than these other things. We're much better at predicting it. The foundation of this framework is a library of coupled numerical models that simulate the Earth's physical processes. So rather than just having one setup, you could have multiple setups, and researchers can probably come in, test them, and figure out which ones are better or make improvements to them. There's also include some algorithms for assimilating, which means putting data into the model, of assimilating this observational data into a form that can be used in initial from single number or ensemble prediction systems, and also in all of these different coupled models. Coupled meaning they work and interact with each other. I currently believe, based on what I've heard, MPAS-Core will be used for GFS, and UFS will replace will replace GFS. UFS, I think, will have the same capabilities as GFS, but it will allow for the inclusion of a fully coupled weather prediction, and hopefully it can, include and resolve all known physical processes. Now, GFS does have some coupling with it, but I think this system will be much more efficient. Also, UFS will improve organization of coupling communication between different models and multiple processing units. Like some of the models might be split up into multiple processing, while other ones are not split up into as many processors, and all of these models have to interact with each other and communicate with each other, which currently in GFS is kind of messy. Also, it has community model capabilities, which basically means researchers can apply it for their research rather than it just being available for national weather prediction. Researchers can go in and they can actually make improvements, which can later be accepted in future updates. Also, I hope that this also means there will be flexibility for regional modeling researchers, as of myself. Customizable resolution settings is something that's very important. Choice of modeling parameters. Maybe we want to change something, like what is the value of CP or one of the constants in the model. And also maybe we want to use coupling of some outside model that hasn't been used before. And that kind of goes back to the community model capability. So, and also all of the references, by the way, for UFS MPAS will be at the end. So here's a little bit on the US operational NWP lagging behind other international modeling systems, and this is from a paper by MPAS in 2023. Actually, the second paper of a paper that was written in 2006, and this is kind of an update to look at what's changed since then. So Global Model Forecast Skill, or ACC, which stands for Anomaly Correlation Coefficient. Basically, if it's a 1, it's good. If it's a -1, it's pretty bad. We're consistently behind ECMWF, which is another model in Europe. You can see in the plot on top right, red is ECMWF, black is GFS. It's consistently better. Still, GFS is still above a 0.8 now, above a 0.8 now, which is pretty good. But we haven't been able to surpass or even stay on that same level. And you might look at the curve and say, oh, they're pretty close together. Well, actually, I think they're pretty. I think actually they're pretty far apart from each other. Additionally, GFS has these short-term skill losses called dropouts, which you see on the bottom right curve, which the black curve, you see how the ACC dips kind of randomly within short-term intervals. That's a problem, and I think there's been like international competitions for weather prediction, and a lot of the American models have had to pull out in some of them because and not take part because there's some issues with the model. Also, GEFS, the ensemble version, which is a bunch of models combined together and averaged to get a better prediction, is kind of lacking. Currently, I think I have a typo. I think it's just maybe should be 21 kilometers with. Well, I have to apologize. I think there's some typos in here. But currently, just to summarize, ECMWF has better resolution and more ensemble members than we do. And also, we don't have any, convective permitting basing below 4 kilometers for ensembles either, which we discussed earlier. So MAS 2023 also talks about kind of a lot of problems that have caused us to kind of not have caught up, which is redundant efforts among several federal agencies and national groups. Numerical weather prediction is done by NOAA, the Navy, the Air Force, NASA, etc., and it's not really consolidated into one effort. And that doesn't mean only going to one model, because that's you don't want to just be rigid and stick with one model, but I think a system that combines this and one group working together that looks at all the different models even, or combines them and allows for some flexibility, would be really good. Also, there's redundant, non-optimal development, such as, there's multiple models again, rather than just a single model that goes on the same resolution. Like HRRR, the rapid refresh model, is a very high resolution model, but why can't GFS be on that scale? Why can't NAM? NAM is also a pretty high resolution model. Why aren't they the same thing, or organized by the same group? Also, there's also historically a lack of computer resources. For example, before Hurricane Sandy in 2012, they were only using a 0.1 petaflops, which is 1/10 of what is available to ECMWF. And also ECMWF has higher resolution too. I think if you go on windy.com, they usually show it as having 9 kilometers. So that's pretty good. Also, a key deficiency in this NWP by US is the data assimilation. There's kind of not this unified force to kind of just collect the data every time and improve that and put it into the data. Also, the system for assimilating the data with statistics and everything to give us an initial condition for the run. ECMWF uses full 4D VAR. NWS uses 3D VAR, or just an ensemble-based approach, 4D NVAR. They don't use the best approach for that. Recommendations as given by MAS 2023 is, and also some kind of issues. So the NOAA management structure spreads this responsibility for operational modeling over too many offices and individuals, and MAS calls for it to be more consolidated. Also, they want they want an organizational structure to progressively improve its modeling systems over time, and so they called for something called the U.S. Numerical Weather Prediction Center, NWPC, to actually take care of consolidating this. Also, a national data assimilation effort is needed. They could create a state of the science. U.S. could create a state of science national data assimilation system that will organize collecting all this data and improving that collection mechanism, and developing and improving the model over time. there's also some recommendations about what to do for that. And right. And so the MAS calls for a model development division to be established. As for the lack of computational resources, that should be a priority. If there could be better funding and just a single group such as Numerical Weather Prediction Center that pays for the computer, sets up the computer, and sets it up to be done for operational NWP. So they should expand their computational resources and also come up with a plan with concrete examples of how operational prediction could be improved with greater computing capabilities, such as moving the resolution down now that they get that funding and have that better computational resource. Initial community modeling, MAS believes, is extremely important because the research community is one of the groups that makes the most advancements in better representation of physics in these models. So that's something that should be a focus. As for references, we have some references on the website for the National Centers for Environmental Information, Environmental Modeling Center, EMC, also Unified Forecast System, UFS, and it also included the GFS link here, if you want, for the citation, and then MAS 2023, which is called the Uncoordinated Giant Number 2, Why U.S. Operational Numerical Weather Prediction is Still Lagging and How to Fix It. Great paper, not too long as well, and it kind of really has a lot of historical understanding of this issue and a very well thought out way to fix it. And so I think the author is from University of Washington. They also served on several committees that kind of discussed this national weather prediction, numerical weather prediction for U.S. global NWP. He's on several committees that discuss that issue. So thanks for watching and stay tuned for more. Feel free to like and subscribe if you want. Thanks. Bye-bye.